In this video, we're going to look at the Chapter 3 exam review. Question 1 in your exam review asks you to use the vertex and intercepts to sketch the graph of a quadratic function. Give the equation of the parabola's axis of symmetry. Use the graph to determine the domain and range of the function. Since this quadratic function is in standard form, you should be able to just look at it and determine what the vertex is, and then you can plot that point. Looking at this function, I have x plus 1 squared minus 4. So whatever number I'm subtracting from the x is the x coordinate of my vertex. Since I have plus 1 there, I'm actually subtracting negative 1. So the x coordinate of my vertex is negative 1. The y coordinate of my vertex is whatever I'm adding or subtracting from the function. Since I'm subtracting 4, the y coordinate is negative 4. So my vertex is at negative 1, negative 4, and I'll plot that. Next, I need to find an intercept. The easiest intercept to find in this case is the y-intercept, because I just need to evaluate the function at 0. So f of 0 will be 0 plus 1 squared minus 4, which is 1 minus 4, which is negative 3. So the y-intercept is negative 3, and that would be the next point that I would plot. And MyMathLab would then complete the graph of my parabola for me. All right, the axis of symmetry. The axis of symmetry is the vertical line that bisects the parabola. So it's the vertical line that goes through the vertex. I'm going to sketch that in right here as a dashed line. So the equation of that vertical line would be x equals the x coordinate of my vertex, or x equals negative 1. The domain of this quadratic function, the domain of every quadratic function, is from negative infinity to positive infinity, the set of all real numbers. And since this is a quadratic function of parabola that opens up, its range is going to be all values from its vertex to infinity. So it has a minimum value. So the range starts at its minimum value and goes to positive infinity. So that would be from negative 4 to infinity. And I do use a bracket on the negative 4 because negative 4 is a point on the graph of this function. Problem 2, you're given another quadratic function, except this time it's not in standard form. So you will need to use your vertex formula to find the vertex. Part A, determine without graphing whether the function has a minimum value or a maximum value. Part B, find the minimum or maximum value and determine where it occurs. Part C, identify the function's domain and range. All right, looking at this function, the leading coefficient of this function is negative 2. Remember, if your function is written in descending order, then the leading coefficient is the first constant. Since this leading coefficient is a negative number, your parabola opens down. If your parabola opens down, then it has a maximum. To determine the maximum value, I need to use the formula for my vertex. The formula is the x-coordinate of my vertex can be found by taking minus b and dividing that by 2a. In my function, b is 20. So I have negative 20 over 2 times. A is negative 2. Negative 20 divided by negative 4 is positive 5. So my maximum value occurs at x equals 5. All right, but what is my maximum value? To determine the maximum value of this function, I have to evaluate the function at 5. So I'm going to let my calculator do the work for me. I have negative 2 times 5 squared plus 20 times 5 minus 8. So I'm going to take my calculator out and I'm going to do that calculation and I get 42. So the maximum value is 42 and it occurs at x equals 5. The domain of every quadratic function, the domain of every polynomial function is the set of all real numbers. The range, since this is a parabola that opens down, it does not have a beginning point. It continues on forever in the negative direction. So the range starts at negative infinity. And its highest point would be at 42. So the range ends at 42. So the range is from negative infinity to 42. And we do use a bracket on the 42 because the 42 is included in the range of my function. Okay, problem 3 is going to be a matching problem. You're going to be given 4 graphs and you're going to match each graph to the equation. And it's going to be a drag and drop. So you're going to take the graph and drag it to the correct position. Let's just look real quick at the 4 equations that we are given. And let's see if we can't figure out from the leading coefficient test which of these 4 graphs has to be the correct one. So look at 15 there. 15 is f of x equals negative 4x to the 4th plus x squared. That's an even function. Its degree is 4, so it's even. And its leading coefficient is negative 1. So what kind of end behavior does this function have? This function's end behavior is that it will fall to the left and it will fall to the right. The only function, only graph up there that falls to the left and falls to the right is the first one. So this first one, let's circle it in green. This first one has to go here. All right, let's look at 16. We have x to the 3rd minus 4x squared. That is a 3rd degree function whose leading coefficient is positive. If we have an odd function whose leading coefficient is positive, it must fall to the left and rise to the right. And the only one that falls to the left and rises to the right is the second one. So I would drag and drop it into that box. Look at the equation 17, f of x equals x minus 3 squared. That's a quadratic equation, so it's a parabola. Its leading coefficient is positive 1, so it's a parabola that opens up. The only parabola that opens up in the choice in my 4 choices is the last choice, so it has to be the last one. All right, so part 18, or number 18, excuse me, that is a 3rd degree polynomial function whose leading coefficient is negative. If it's odd and its leading coefficient is negative, it must rise to the left and fall to the right, and you only have one left. So it has to be that third one, the one that we haven't used, and it does. It rises to the left and falls to the right, so it has to be that one. All right, problem 4. Use the given function to complete parts A through E below. Part A, use the leading coefficient test to determine the graph's end behavior. And I showed you in class how to determine the leading term of a polynomial when it's in its factored form by just looking at the first terms. So the leading coefficient has to be, the leading term has to be, we're going to take each of these first terms. So we're going to take the negative 4 times the x, but we're squaring the x, times x squared. So that's going to give us negative 4x to the 4th. So this is a 4th degree polynomial function that's even. You can see that from my ugly face underneath. So since this leading term is negative 4x to the 4th, it's an even function whose leading coefficient is negative, so it has to fall to the left and fall to the right. That was my second choice here. All right, to find the x-intercepts, I set each factor that has a variable in it equal to 0. So I set the x minus 1 squared equal to 0 and the x squared minus 4 equal to 0. When I take the square root of both sides of that first equation, I get x minus 1 is 0, so I get x is 1. The second equation, I could either factor that or I could use the square root property. I'm going to factor it. I think it makes seeing the multiplicity a little bit easier if I factor that. So I set those two factors equal to 0, x plus 1 equal to 0, and x minus 1 equal to 0, and I get x is negative 2 and x is 2. So my x-intercepts are 1, negative 2, and positive 2. All right, now they're going to ask me about what the graph does at each of these intercepts. The first question is where the graph crosses the x-axis. And the graph will cross the x-axis when the multiplicity of my 0 is odd. And that second equation, x squared minus 4 equals 0, I factor to x plus 2 times x minus 2. And each one of those factors has a degree of 1. There's an understood exponent of 1 there. So the multiplicity of those two x-intercepts is odd. It's equal to 1. So it's going to cross the x-axis at negative 2 and positive 2. Now the multiplicity of the x-intercept 1 is 2, because the factor that I got that 0 from, x minus 1 squared, the exponent on that factor is the number 2. That's an even number. So the graph is going to touch the x-axis at the 0, 1. All right, the next thing it wants me to do is to find the y-intercept, and I find the y-intercept by evaluating this function at 0. So I'm going to do that. So that's going to be minus 4 times 0 minus 1 squared times 0 squared minus 4. Okay, so I get negative 4 Negative 1 times negative 1 is positive 1 times negative 4. 0 squared minus 4 is negative 4. Negative 4 times negative 4 is positive 16. So the y-intercept is 16. Then it asks me about symmetry, and to determine symmetry, I evaluate the function at negative x. So I get negative 4 times negative x minus 1 squared times negative x squared minus 4. That's going to be negative 4 times minus x minus 1 squared. Negative x squared is x squared. And then I look at what I get when I've done this. And this is not the same function that I began with. So it does not have symmetry with respect to the y-axis. And it's not exactly the opposite of what I began with. So it does not have symmetry with respect to the origin. So the answer is neither. And I think you could also look at the 4 choices they give you down there for graphs. None of those 4 choices that they give, well, maybe B. B looks like it has symmetry with respect to the y-axis. But B doesn't fit the criteria that I need to determine which one of these is the graph. So it's not going to be B anyway. So there isn't going to be any symmetry for this particular function. All right, so now we do need to determine the graph. And you can do this one of 2 ways. First of all, you have all the information you need to be able to look at these 4 graphs and figure out which one it isn't. It's not going to be that one because it doesn't have the correct end behavior. It's not going to be D because D also doesn't have the correct end behavior. It's not going to be B because B doesn't have the correct behavior at the x-intercepts. This graph actually touches, and turns around at x equals 1. That graph doesn't do that. So the only graph it can be is C, and C does not have any symmetry. All right, the next question, we start our division. I believe we started this, what was this, in section 3.3, I think this was. All right, so let's see if we can't divide using synthetic division. Now, to be able to divide a polynomial by another polynomial using synthetic division, you have to have all the terms in your dividend. So if you have any terms missing, you need to write those in using coefficients of 0. So my dividend is x to the 5th plus 9x to the 3rd minus 10. And I do have missing terms. The x to the 4th term is missing, the x squared term is missing, and the x term is missing. So I do need to rewrite this. So I'm going to write this as x to the 5th plus 0x to the 4th plus 9x to the 3rd plus 0x squared plus 0x minus 10 divided by x minus 1. So now I can set up my synthetic division. So my divisor is 1. I'm going to write down the row that's the coefficients on my dividend. Make sure I have those all written down correctly. That looks correct to me. So I bring the first 1 straight down. Then I multiply quotient times divisor. 1 times 1 is 1. I write that under the next term in my dividend, and I add 0 plus 1 is 1. 1 times 1 is 1. Write that under the 9. 9 plus 1 is 10. 10 times 1 is 10. Write that under the 0 and add 0 plus 10 is 10. 10 times 1 is 10. 0 plus 10 is 10. 10 times 1 is 10. My remainder will be 0. The last number in the 3rd row of my synthetic division is my remainder. And I'm not sure that I have room in this little space we have here, but I'm going to see if I can write this right underneath it. All right, I've divided a fifth degree polynomial function by a first degree polynomial function. So I'm going to get a quotient that's a fourth degree polynomial function. And each of these numbers in the third row of my synthetic division is the coefficients on this fourth degree polynomial function. So the first number is the coefficient on the x to the fourth. The second number is the coefficient on the x to the third. The third is the x squared. The fourth is the x. The last is the constant. And my remainder is 0. So it's x to the fourth plus x to the third plus 10x squared. And you'll have more room when you type this into MyMathLab. Plus 10x plus 10. All right. The next problem is to start finding the zeros of polynomial functions. And they give you a graph of your polynomial. So by looking at the graph, you can determine the first zero. And you can do this for any polynomial that has a real zero that's an integer or a rational number. You can take your calculator out and graph it and determine what the first zero is. And in this case, looking at our graph, it appears that that's 3. So the first zero of my polynomial function is 3. So the first solution is the number 3. So you should be able to get the first part of this question correct by just looking at the graph. Now, this polynomial is going to have a couple of more zeros. So how do I determine what those zeros are? Well, I'm going to use synthetic division. I'm going to divide this polynomial by 3. So I'm going to write down the coefficients in my dividend. Make sure I have those written down correctly. Looks good. Bring the 1 straight down. 1 times 3 is 3. 4 plus 3 is 7. 7 times 3 is 21. Minus 11 plus 21 is 10. 10 times 3 is 30. And my remainder is 0, which is what I expected to happen. All right, so this third row gives me the quadratic factor of this polynomial function. So I can set that equal to 0. And find the other two zeros. You can factor it or use the quadratic formula, whatever you want to do. I'm too lazy for that quadratic formula, especially when it looks fairly easy to factor. That looks correct. 2x and 5x is 7x. 2 times 5 is 10. So we're going to get what? -2 and -5. So the other two zeros are -2 and -5. All right. Question 7. You're now going to find the zeros of a polynomial function using everything that you've learned thus far. So this is section 3.4. The first thing it wants you to do is make a list of all the possible rational zeros of this polynomial function. And to determine the list of rational zeros, you take factors of your constant over the factors of your leading coefficient. And in all of these, we're not going to make this difficult. The leading coefficient is going to be the number 1. So you really only need to list all the factors of your constant. And your constant here is 20. So you need all the factors of the number 20. So plus or minus 1 would be a factor of 20, as would 2. 3 is not a factor of 20, but 4 is, so plus or minus 4. 5 is a factor of 20, so plus or minus 5. 6 isn't, 7 isn't, 8 isn't, 9 isn't, but 10 is, so plus or minus 10. 11, no. 12, no. 13, no, 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 no. The next factor of 20 would be plus or minus 20. So there are all the possible rational zeros of my polynomial function. The next thing you're going to do is start using synthetic division to test these rational zeros to see if one of them is a zero. So I'm just going to scroll down where I've got some white space here, and I'm going to divide this polynomial first by 1. I always start with 1. Okay, so my dividend was 1, -5, -4, and 20. Bring down the 1. Okay, my remainder is not 0, so 1 is not a 0 of this polynomial function. So I'm going to try 2. Now I could try -1, but I got a sneaking suspicion it's 2. So I'm going to try 2. Okay, bring down the 1, 2, -3, -6, -10, -20, and that is going to work. Because my remainder is 0, then 2 is a 0. So part B, one rational root of the given equation is, well, I determined that 2 is a rational 0. So I would type in 2. Now part C, we're going to use that root. We've done synthetic division so we can find the quadratic factor. Then I can find the other 2 zeros. So I'm going to write the quadratic x squared minus 3x minus 10 equals 0. I'm going to factor that to -5 plus 2. So what am I going to get? X is 5 or -2. So the other 2 zeros are 5 and -2. So my 3 zeros would be 2, and then the other 2 would be -5 and 2. So my zeros are 2, 5, and -2. And I do need to type all 3 of those numbers in that second part, that part C, excuse me. All right, problem 8 is Descartes' rule of signs. And to use Descartes' rule of signs, the first thing you do is look at the function and determine the number of sign changes you have in the function. All right, so from negative to positive gives me 1 sign change. From positive to negative gives me 2 sign changes. From negative to positive gives me 3 sign changes. So Descartes' rule of signs says that I could have 3 positive real zeros, or I could have that number -2. So I could have 3 positive real zeros, or I could have that number less 2. 3 minus 2 is 1. So this function either has all 3 of its zeros are positive numbers, or one of its zeros is a positive number. Now we look at f of -x. So I'm going to evaluate this function at -x. And when I evaluate this function at -x, every term of odd degree will change sign. That's because you're raising a negative to an odd power, and it will be negative. So you'll change the sign of the term. So when we evaluate this at -x, we get 2x to the third plus x squared. The sign of terms of even degree will not change, because if you raise a negative to an even power, it's going to be positive. Okay, there are no sign changes here. No sign changes. every term is positive. So there are no negative zeros. So if we were to find the zeros of this function, one of them will be positive. The other two could be positive, or they might be complex. And I don't really know until I get in there and try to find those. But I do know that none of them will be negative. Now, the advantage of Descartes' rule of signs is, looking at this, I could determine the possible rational zeros. It would be factors of 6 over factors of 2. But I don't need to plus or minus anything because none of the zeros are going to be negative. So all the possible rational zeros that I would test would be positive numbers because no zeros are going to be negative. All right, problem 9, we're going to find the zeros of this polynomial function. And it asks you to use the rational zeros theorem. It tells you to use Descartes' rule of signs, maybe graph it. And I am not going to grade you on what you use, but you do need to use something to find the first zero. Whatever you want to use. You can graph it and find the first zero. Descartes' rule of signs tells me, looking at the sign changes, what do we have here? 1 sign change, 2 sign changes. So we have 2 or no positive zeros. And look at f of negative x. That looks like 1 sign change. So I do know one of them is negative. So absolutely positively one of these zeros is a negative. So maybe I graph it and see where it crosses the x-axis in the negative direction and figure out what that zero is. You could do that. Now the rational zeros are going to be factors of 15, my constant. So what's that going to be? Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So one of those numbers is possibly a zero of this thing. Now, even if I don't look at the rational zeros or Descartes' rule of signs, I always check to see if 1 is a zero. It's the easiest number to test, so check it first. If it doesn't work, then just work your way down. Check 3, then check 5, then check 15. If none of those are zeros, which one of them probably is, but if none of them are, then start checking negative 1, negative 3, negative 5, and negative 15. You can do this really quickly using synthetic division. So I'm going to test 1. And I'm going to do that synthetic division. So my coefficients on my function are 1, negative 3, negative 13, and 15. Bring the 1 down. 1 times 1 is 1. Negative 2. And that's sure enough, 1 is a 0. Since the remainder of my synthetic division is 0, then 1 is a 0 of this polynomial function. So my other factor is x squared minus 2x minus 15. I'm going to factor that to minus 5 plus 3. So I get what? 5 and negative 3. So my 3 zeros are 1, 5, and negative 3. And let's just quickly discuss that Descartes was right. Descartes told us that one of the zeros was negative, and one of the zeros is negative. And then we have the possibility of 2 or none of them being positive. Well, as it turns out, 2 of them are positive. All right, let's now move to our rational zeros. our rational functions, I will spit it out. We're going to use the 7-step graphing strategy to graph this rational function. And you do have to walk through all 7 steps because there are 7 parts to this particular problem. Okay, so the first thing you do is to determine if there's any symmetry. And I'm not sure that there is on any of these problems symmetry. But to determine the symmetry, we evaluate the function at -x. All right, that is not the same function I started with. It's also not exactly the opposite of the function I started with, so there is no symmetry. All right, the next thing we need to do is to find the y-intercept. And to find the y-intercept, we evaluate the function at 0. And MyMathLab will count this incorrect if you don't simplify it. So if you don't remember how to simplify fractions, there's a common factor of 5 here. And negative divided by negative is positive. So this is 1/5. Take your calculator and do it on your calculator. 5 divided by 25. And then change that to a fraction. Let your calculator do it if you can't remember how to do it. So the y-intercept is 1/5. All right. Now here comes the kind of tricky part that you really need to be careful with. What are the x-intercepts? Now let me write that function down again so we can see it. Now typically with a rational function, the way we determine the x-intercept is to set the numerator equal to 0. Well, that's a problem because x can't equal 5. X cannot equal 5 because if you put x equals 5 into the denominator of this rational function, the denominator is 0. You can't do that. So if the value you get for your x-intercept is a restriction on the domain of your function, there is no x-intercept. So there is no x-intercept. All right, so the next part is to determine the asymptotes. And to determine a vertical asymptote, you have to factor this function and cancel any common factors. So this factors 2. The denominator is one of your special products. It's the difference of 2 squares. So it factors to the sum times the difference. The x minus 5 will cancel. So you get 1 over x plus 5. And to find the vertical asymptote, you set that equal to 0. So x equals -5 is my vertical asymptote. But there is a hole at x equals 5. X cannot equal 5. If x equals 5, then you have division by 0. You can't do that. So there's an asymptote at -5 and a hole at x equals 5. So we choose part A, where we have a vertical asymptote of x equals -5, but we have a hole at +5. Next is to determine the horizontal asymptote. Our function was x minus 5 over x squared minus 25. So our numerator degree was 1. Our denominator degree was 2. Since our numerator degree is less than our denominator degree, the x-axis is a horizontal asymptote. So y equals 0 is a horizontal asymptote. The next step in this problem is to evaluate this function at 5 different values of x. Let your calculator do this for you. If you can't convert a decimal into a fraction, let your calculator do that. Every calculator, every scientific and graphing calculator has a button somewhere on it that will convert a decimal to a fraction. Or if you're using any of the TI models, either scientific or graphing, they actually have a fraction button on your calculator, so you can use that too. So I'm going to go ahead and tell you what these values are, and then I'm going to let you find them. I do believe if we evaluate this at -8, we get -13 over, what is that, 64? Is that 39? So I think this is -1/3. At -7, I believe this is -1/2. Or it's 1/9, 1/11, and 1/12 is what I calculated. And I highly recommend you just take your calculator out and practice this. You should be able to evaluate a function at a value using your calculator. All right, now last but not least, which of these 4 is the graph? All right, using all the information that you had from above, you can determine which one of these is the correct graph. All right, it cannot be A. And it cannot be A because the vertical asymptote is at x equals 5. So that is not the graph. Your vertical asymptote is at x equals -5. So it's not A. Look at B. It's not B because your horizontal asymptote was the x-axis. Graph B has a horizontal asymptote that is above the x-axis. It's not B. Look at C. Can't be C. C has a horizontal asymptote below the x-axis. It has to be D. And it has to be D for a couple of reasons. Number one, the asymptotes are in the correct place. The vertical asymptote is at x equals -5. The horizontal asymptote is the x-axis. This graph also has a hole at 5. So this is the correct graph. All right, the last 2 problems on the exam are from the last section in chapter 3, section 3.6, where we looked at quadratic and rational inequalities. To find a quadratic or a rational inequality, you must first find boundary points. And you find the boundary points of a polynomial inequality by setting the polynomial equal to 0 and solving the equation. So we take the 5x² plus 9x minus 2 and we set that equal to 0. And we solve that equation. And I am going to factor it. 5x plus 2 minus 1 equals 0. So it looks like 1/5 and -2. All right, so now that I know my boundary points, I'm going to set up my number line. And so these 2 boundary points are going to separate my number line into 3 intervals. The first interval is going to be from -∞ to -2. The second interval is from -2 to 1/5. And the third interval is from 1/5 to infinity. And I'm actually going to use brackets on all of these endpoints because my inequality is less than or equal to. So I'm going to go ahead and set up my intervals and pick my test values and see if I can't determine what the solution is. So let me see if I can write this over here. So my intervals are from negative infinity to -2, from -2 to 1/5, and from 1/5 to infinity. Okay, let me pick a test value. Oh, -3. A 0 is between -2 and 1/5, so I'm going to use 0. And what's a number bigger than 1/5? 1. And then I'm going to evaluate the function. All right, when I evaluate the function at -3, I get 16. That's greater than 0. So that's not a solution, because my inequality says it has to be less than 0. So the first interval is not a solution. When I evaluate this function at 0, I get -2. Well, that's less than 0. So that is the solution, from -2 to 1/5. I'm going to go ahead and check that last interval. If I evaluate this function at 1, I get 12. 12 is greater than 0. That is not a solution. So the solution to this inequality is any number between -2 and 1/5. Okay, so which of these 6 graphs is the graph of my solution? Well, I think the only one that looks like it's going from -2 to 1/5, including -2 and 1/5, would be D. All right, our last problem on our exam. Solving a rational inequality. Now, the only difference between solving a polynomial inequality and a rational inequality is how you find the boundary points. This rational inequality is going to have 3 boundary points, because to find the boundary points, you set the numerator equal to 0 and you set the denominator equal to 0. So I get -12, 14, and -10. Okay, so I'm going to draw my number line real quick here. So we have -12, -10, and 14. So this is going to separate my number line into 4 intervals. The first interval is from -infinity to -12. From -12 to -10. From -10 to 14. And from 14 to infinity. All right, so brackets or parentheses? Well, it depends. This rational inequality is a less than or equal type inequality. So you're going to put a bracket on anything that would make the numerator equal to 0. You are going to put a parenthesis on anything that would make the denominator 0. So you're going to put parentheses next to the -10, because if x were -10, you would have division by 0, and you can't do that. So I'm going to bracket -12, I'm going to bracket 14. All right, so we are good to go. So I'm going to go down here where I got some white space, and let's set up our test intervals. So we have the interval. We have these 4 intervals from -infinity to -12, from -12 to -10, and you'll note I've got a parenthesis on that -10, because if x were -10, that would cause division by 0, and I can't do that. So I'm going to exclude -10 from my solution. What do we have? From -10 to 14, and from 14 to infinity. All right, now let's pick a test value in each of these 4 intervals. Negative 13 is less than negative 12. Between negative 12 and negative 10, negative 11. 0 is between negative 10 and 14, so I'm going to pick that. That's the easiest one to test. 15 is bigger than 14. Okay, so I'm going to take my handy dandy calculator out. And I'm going to let my calculator evaluate each of these. The function evaluated at negative 13 is negative 9. Well, that's less than 0. Okay, so at negative 11, we get 25. That's greater than 0. At 0, we get negative, what do we get? Negative 84 fifths is what I got. Well, that's less than 0. And at 15, I got 27 25ths. Well, that's greater than 0. All right, so what am I interested in? I'm interested in where this is less than 0. Well, it's less than 0 here. And it's less than 0 here. So the solution to this rational inequality is the union of those two sets. So it's the union of from negative infinity to negative 12, from negative 10 to 14. All right, so now let's look at the graphs. Which of these 6 graphs describe the union of the two sets from negative infinity to negative 12 and from negative 10 to 14 with a parenthesis on the negative 10? I think that looks like A. How about you? Does that look correct? Can't be any of the other 5 graphs. All right, and that is the end of our review. There are 12 problems on this exam, so please do the review. I hope you find this video helpful as you go through the review yourself. Thank you.